Hello everybody, this is Dr. Ali Mugebel. Today's topic is narrowband noise, and this is part of the Modern Digital Communication Systems course. The outline of today's lecture is the following. We'd like to go over narrowband noise in canonical forms. Later on we'll address polar form. We'll look at the properties of quadrature components of narrowband noise. We'll look at ideal bandpass filtered white noise and RLC bandpass filtered white noise. Just like we have covered the canonical form, we'll look at the polar form, and then we'll conclude with an example of sinusoidal wave and narrowband noise. So what is narrowband noise? Narrowband noise, let's start by defining what a bandpass signal is. A signal G of t is a bandpass signal if its Fourier transform is non-negligible only in a band of frequencies of total extent of 2W, that's twice the bandwidth. Once your signal is modulated or bandpass signal, the bandwidth is referred to as 2W, say centered at the carrier frequency Fc, where Fc is the carrier frequency. So if it has non-negligible only at this band, so if this band is negligible, the baseband, there is no strong signal, we call it a noise, we call the signal bandpass signal. Now, in majority of communication signals, we find that the bandwidth, which is W, is very small. This width is very small compared to the carrier. This is just for explanation. Otherwise, if you extend this, you'll find that the bandwidth, the extension of the signal relative to the center frequency is little. And this is why we call it narrowband. So the issue of being narrow is relative to the center or to the carrier frequency. The noise random process that appears at the output of a narrowband signal is a narrowband noise. So we can see that there is a relation with narrowband signals, we get narrowband noise. The noise random process appearing at the output of narrowband filter, where bandwidth is just large enough to pass the signal of interest, is called the narrowband noise. So this concept of narrowband noise comes with the concept of narrowband signal. Now, just to illustrate here, the narrowband noise, since it's shifted, it's modulated with the carrier, then it can be expressed in two different forms, canonical form or polar form. Remember that this is the signal of interest, but because of the noise, the additive noise, we will get the received signal will be the resultant, which is the signal plus noise. Now this noise vector, which is here, can be decomposed into two component parts, which is the M phase, shown in green, and the quadrature component. Alternatively, you can think of the noise vector as envelope or magnitude and phase. So this is the noise. The noise can be represented as envelope and phase. I am using the same color here to match. The green goes with the M phase, and here the red goes with the quadrature component. And similarly for the polar format, we have the purple and the orange colors. Now for the narrowband noise in canonical format, let's focus. So this noise can be represented as sum of two signals, and we would represent that with the low pass equivalent. So the canonical form of the representation of narrowband noise, we can think of this as, because it's modulated, we can think of like the QAM case. We have the M phase component and the quadrature component. So this noise can be decomposed into two parts. One is scaled by cosine, another one is scaled by minus sine, where Ni and Nq are the M phase and the quadrature components of the narrowband noise, respectively. Both components are low pass because this is before modulation, so those are low pass equivalent. We can also reconstruct or decompose the signal. So this is generation of narrowband noise, and here with the decomposition of the narrowband noise. So if you multiply by cosine again, I need 2 to adjust the scaling, and then we have a low pass filter, and in that case this is like modulation, and this is the demodulation process. If you want the exact magnitude, you need to scale by 2. Remember that this is defined with a minus sign as a standard notation, and here we have the minus sign to recover the correct signal. So what we have in this slide is the canonical form representation of narrowband noise. Here are some properties of the quadrature component of the narrowband noise. Both the M phase and the quadrature components has zero mean as the original narrowband noise and same variance. In fact, it would have similar power spectral density. Not exactly, of course, because some of them, these are low pass and this is bandpass signals or passband signals. If the narrowband noise is Gaussian, then the components are jointly Gaussian, not just individually Gaussian, but they're also jointly Gaussian. If n of t is wide sense stationary, then the components are jointly wide sense stationary. And we mentioned that the power spectral density of the components will be the same, and it is similar to the noise itself, Sn, but of course it should be shifted because this is passband signal or bandpass signal, and we need to shift it back to the origin. So you can recover the signal, the components, by shifting the power spectral density, and that's the range of valid frequencies. The cross spectral densities are purely imaginary. So we got the following. You know that there's a minus sign difference here. The order is important here for the cross correlation or cross power spectral density, and it's going to be purely imaginary because of the orthogonality, the difference between the two. There's a 90-degree difference between cosine and sine. If a narrowband noise is Gaussian with zero mean and power spectral density n, that's locally symmetric around Fc, then if it turns out to be symmetric around the carrier, then you can say that these components are going to be statistically independent. You might need some of these features, some of these properties, as we address topics related to the performance of different communication systems with narrowband noise. Now let's take two examples. The first one is the power spectral density of an ideal bandpass filtered noise. So if you have white noise, the white noise has constant power spectral density. But remember, when we go through an ideal, this time bandpass filter, this formula is always correct. The output equal to the input power spectral density multiplied by the square of the transfer function. So if you go through the filter, what remains from the constant in over 2 is only this 2 bands. And because the filter is ideal with gain 1, amplitude response 1, so square of 1 is 1, I will get the following. So this is the output, this is the spectrum of an ideal bandpass filtered white noise. You should be able to redraw it yourself. It's centered around Fc and the bandwidth is 2b. Sometimes we use W and sometimes we use B, and the scale will be n0 over 2. We can write this expression mathematically by saying it's n0 over 2, that's the scaling factor, and then we have two rect functions shifted, one to the positive, one to the negative, and divide by the width of the rect. So this mathematical notation, and this is the graphical representation of the power spectral density. Notice that we started with the frequency domain because we are dealing with filters. So filters are well defined in the frequency domain. So when I say ideal bandpass filter white noise, you should be able to draw the expression, draw the figure, or write the expression. Now we have presented the power spectral density, and now it's time to look at the autocorrelation. Remember that they are inverse Fourier transform of each other, so I can find the autocorrelation by the inverse Fourier transform. Notice we have a plus sign here, and if you perform the integration and execute the integration, you will find, as we know from before, that we have a rect will give you sinc, and because of the shift, it will be sinc multiplied by a cosine. If you want to do this in slow steps, then you integrate over the two squares, substitute, and then you know that we can go using Euler identity from exponential to cosine, and there we go. We can sketch the autocorrelation function like this. It is a rect, a sinc with the following properties, and it's filled with cosine. It's a modulated, if you like, modulated sinc. And the exact values are given here. At tau equal to 0, cosine is 1, and sinc is 1, and you get 2 n0 times b. This is important because this says that a narrowband filtered noise, filtered ideally, will be positively correlated, negatively correlated, and at times it's uncorrelated. And at times it's uncorrelated. So if you look at these points, you can select the sampling intervals which cause uncorrelation. So from here to here we have 1 over B, and from here to here 1 over FC. So we can say, from the previous discussion, the in-phase and the quadrature components of the narrowband noise has the following properties. Okay, I can extract the baseband equivalent or the low bass band equivalent, and of course the rect will give you sync. So this is the low bass equivalent of the bandpass filtered white noise. And of course the autocorrelation for the low bass equivalent will be just sync. That's bringing us back to the low bass filtered noise, which we had in a previous lecture. All right, and here we see the spectrum of the ideal filtered white noise. Okay, we are done with the ideally filtered white. We are done with the ideally filtered bandpass noise, and now look at the RLC of bandpass filtered noise. This is the RLC circuit. It will give you bandpass filter, and the transfer function is given by the following. It's a voltage divider that will be R 1 over j omega c and j omega l, or j2 by fl, and by using voltage divider it's going to be R over the sum of the impedances. If you want to find the output, then you need to square this, and if you want, we may approximate the transfer function of the bandpass filter as the following. This is an approximation where this is just a Q factor, so we can write things in terms of the center frequency and rewrite the expression in a different way. This is how the the bandpass RC filter looks like. It's not ideal, it's not square. Now, this is the expression that we just mentioned before, and for the noise it will be scaled by n naught over 2, and times this squared, of course, times the square of the denominator. If you square the denominator, you get the following expression. This is why we go from the j will disappear here, and we have q squared. So this is the power spectral density of the bandpass filtered noise, and the low pass equivalent will be by removing the carrier shift. So if you remove the carrier shift and reorganize things, you will find that we can write this in terms of n naught over, of course, you remove the shift, and there is a scaling factor, of course. So we have the power spectral density of the bandpass filtered noise, and we have also the power spectral density of the low pass equivalent. Narrowband random noise in polar format. In addition to the canonical format, we can represent the signal, this is the canonical format. It's like Cartesian format. We can represent magnitude and phase. And the magnitude, we know how to go from one format to another. It's equal to the square root of the square of the real and the imaginary part. While the angle is the tan inverse. We already have a minus sign here, so it's going to be a tan inverse imaginary over real. Now we need to see, if these are Gaussians, what would be the distribution of the magnitude. Now let Ni and Nq represent the random variables obtained by observing the noise process in I and Q, respectively at fixed times, which are zero mean and independent Gaussian random variables with variance sigma square, and their joint probability density function is given by the following. This is the canonical format. We would like to know what is the distribution for the case of the Cartesian or the polar format, sorry. So this is how the joint BDF look like. It's a 2D. Now the narrowband random noise in polar format, remember that we need to represent Ni and Nq in as R times cosine psi. This is R and this is psi. And we can also represent the differential. So the probability volume of the random R and psi is given by the following. We want to do kind of change of variable. If you want to integrate this, then you need to replace the variables dni and dq by r dr d theta. So these two guys, if you like, these will be replaced by r, and this is because of this equivalency here. And of course, what is inside here will be replaced by, as we know, by r squared. And now if we continue the representation, we can say that the PDF itself in terms of r and psi can be given by the following expression. Okay, and we can integrate over the two cases. The two, of course, psi does not show explicitly here because of the uniform assumption, and we can say that we can prove that this is double integral will give you 1 to be a valid PDF. So the corresponding joint PDF or PDF probability density function of r and theta is given by the following expression, and we are multiplying by, this is multiplied because they are independent and it's uniform, so we can separate them some way. If you want to separate them, you integrate from 0 to 2 pi. This is a joint, and of course you're scaling by 1 over 2 pi, so this is going to be r, as if we are just deleting the 2 pi. So where the marginal probability density function is uniformly distributed, and the marginal probability density function of r, we integrate from 0 to 2 pi d psi, and we got the following expression. The derived marginal distribution, this distribution is known as the Rayleigh distribution. So although the canonical form are jointly Gaussian, the envelope will be Rayleigh distributed. Okay, and if you want to find the marginal of psi, of course it's going to be uniform, and we know it's going to be 1 over 2 pi. Here how the normalized Rayleigh distribution looks like. So we are representing the envelope, so it's not Gaussian, and it's going to have the following shape. The envelope will not be negative, so this supports our expectation. R is a parameter, so it could change, the shape could change according to R. Now let's look at this example, sinusoidal wave and narrowband noise. Let the received noise given by the following, and we are adding noise to it. N is a noise, it's a narrowband Gaussian noise. I can split. Now we're saying I don't have just noise, I have a sinusoidal with noise. I can represent the noise in terms of canonical format. So it has two parts. One is the M phase and one is the minus N, the sine cosine. The M phase and the quadrature component. Now we'll collect the similar terms together. You can call this Ni prime minus Niq. I can represent that now by saying that this part are Gaussian, they are statistically independent with mean equal to A, because we are adding A to 0 mean, and 0 respectively. The mean here is 0, the mean here is A, because this mean is 0, plus A, so the mean will be A, and the mean of this guy is going to be 0 respectively. The variance is the same, sigma squared, for both the two scenarios, because adding just a mean will not change the variance. Adding a constant number will not change the variance. Now we can think of the normalized Gaussian variable. The joint probability density function for random noise is given by the following expression. And remember that we have now our first term is different. Now if we do the proper transformation, we're not going here into the details of the math. The joint probability density function is given by the following expression. Now the difference here is that we have a sinusoid plus noise, not just noise. Okay, so we have one distinct carrier signal. Okay, you can see now that R and psi are not statistically independent, and the marginal probability density function is difficult to find. So if we just substitute for R here and A, you will find out that we cannot separate them, and we are stuck with the joint PDF. Okay, if you want to find the derivation for the marginal, of course it will have some Bessel function that might be beyond the scope of what we want to do now. But if you are interested, for your information, you can. It's beyond the scope of an undergraduate course, but it is for a graduate course. Now this is just to show you the approximate distribution of the Rician for R equal to 0. Or for different parameters where A is equal to A over, this is the magnitude of the Gaussian function. So the distribution will change as we increase the Gaussian distribution. Okay, so this is just to show you how the Gaussian look like and how the Rician distribution look like. Case for approximation of the marginal of the PDF. We can approximate this if the received signal is much greater than if it's almost noisy. So A is a very small, the added carrier is small, which goes back to our original Rayleigh distribution. So it's going to be Rayleigh distributed if we have small value. Now if the opposite, we have R is very small compared to A, so we have a very high signal to noise ratio, and then we can approximate the PDF with the following, because basically we can ignore part of the noise. So we can approximately Gaussian for R equal to A. If you make R equal to A, you get Gaussian again. So these are just special cases. So we started with Gaussian for the M phase and the quadrature component, and we found out that for the envelope it's going to be Rayleigh, and if it's a sinusoidal plus noise, the envelope will be Rician, as we have seen. Okay, that's just in a summary of what happened to a bandpass filtered noise.